have this room until 12, and then we can extend anything. Sure.
So welcome back, everyone. I propose that we continue again. Before the break, we were discussing this S-lemma by Jakubowicz, which treated these two quadratic forms. But I already explained before the break that, in principle, this theorem would not be enough to apply to our situation, because in our situation, we always deal with matrices being multiplied with these matrices M and N. In particular, matrices of the form identity A transpose B transpose. So we need an extension of this classical S-lemma. And that's how I continue now. So, well, first of all, I should say that I'm enjoying the food in India very much. So I think the person preparing the food at the guest house has a very good cookbook, or maybe he does it all by himself without using any cookbook, I don't know. But we also have a cookbook, and that's a cookbook for data-driven control problems using noisy data. We wrote that a couple years ago. And from that cookbook, I now take one theorem. So it's the following. So I study matrices M and N, they're both symmetric, and I partition them in the following way. So M is partitioned like this, M11, M12, M21, M22. And M11 is Q by Q, M22 is R by R. Of course, since this is a symmetric matrix, also M12 is M21 transpose. In a similar way, also I partition the matrix M. I need to assume two things on the matrix N. In particular, I will assume that N22 is negative definite, and the Schur complement of N with respect to the 2-2 block is positive semi-definite. So N11 minus N12, N22 inverse, N21 is positive semi-definite. Under these two assumptions, then the following holds. So this quadratic inequality, so identity over Z transpose M identity over Z, is positive definite for all matrices Z, such that this quadratic matrix inequality holds if and only if there exists this scalar alpha greater or equal to 0, such that M minus alpha N is positive definite. Oh, very nice, huh? Because the condition that you see over here in this theorem is the same as the one Jakubowicz obtained. Namely, there must exist some alpha such that this linear matrix inequality holds. But now, under these conditions on the matrix M, you see that that linear matrix inequality is in fact equivalent to an implication, not with these quadratic forms, but using these quadratic matrix inequalities. So all solutions to this quadratic matrix inequality in green are also solutions to the quadratic matrix inequality in blue, if and only if there is this alpha, such that m minus alpha n is positive definite. And that's going to help us in the data-driven context. Any questions about this theorem? Is it clear to you what it means? So all solutions to one quadratic matrix inequality are also solutions to another one, if and only if this linear matrix inequality has a solution alpha. That's the point. Well, I want to discuss this theorem a little bit further before really applying it in the data-driven control context. First of all, I want to understand a little bit more what this assumption on the Schur complement on n means. So remember, we're making these two assumptions, right? N to 2 must be negative definite, and the Schur complement must be positive semi-definite. So what does it mean that the Schur complement is positive semi-definite? I want to understand that a bit better. So the first thing I claim here on the slide is that for any matrix Z, I can write this quadratic term over here as this formula on the right here. Now, that's not something we directly see here, but let's work it out on the board. So what do? Well, first of all, I'm going to write down the matrix N as a product of three matrices. Well, what are these matrices? Well, the one in the middle is a block diagonal matrix containing the Schur complement, in the upper left corner, and the matrix n to 2 in the lower right corner. Then I need to multiply with these matrices. Over here. And the transpose of the matrix on the right, which is 0 here, and 1, 2, and 2, 2 inverse. Okay, let's see if I didn't make a stupid error here. Actually, Kanat made a nice suggestion yesterday that one should never do calculations in public. So unfortunately now I'm going to violate that, and it may hurt me. But okay, let's see if this is indeed true. So I compute this product, right? So we have this first matrix, identity, identity, 0, n, 1, 2, n, 2, 2 inverse, times now this product of the second and third matrix, which is n11 minus n12, n22 inverse, n21. Then I compute this, which is n22 times n22 inverse, so that drops, and I get n21. Then I get 0 here, and n22. Okay, good, let's keep going. So let's compute this product. Okay, this is nice. Because if I now compute this first column block and I multiply with this first row block, I get the Schur complement, but I add this term n12, n22 inverse, n21. So I drop this minus the second term over here. So I just get n11 here. Then I compute n21, and then n12, and n22. Yeah, okay, good. So indeed, my claim was correct. This partition matrix N can be decomposed as a product of these three matrices. Okay, good. Yeah, I use that then to work out this quadratic term over here. So, I start with identity over Z, transpose N identity over Z, using the partitioning of N over here and my formula. This is equal to, well, we had this matrix in the middle. Like that. Right. And the I over Z I multiply now with this matrix, so I get I n to 2 inverse n to 1 plus Z. I'm simply computing the product of I over Z times this matrix on the right. Yeah, and then on the left, I just get the transpose of that matrix on the right. So that's identity over n to 2 inverse n to 1 plus Z. Great. Okay. Final step. Let's compute the product. So I multiply identity with the Schur complement and identity, so I get the Schur complement. Like that. And then I have the additional term, which is n to 2 inverse n to 1 plus Z transpose times n to 2 times n to 2 inverse n to 1 plus Z. Like that. And that's exactly the one slide.
Neither positive definite nor negative definite.
Yes. Capital N is not definite in general. True. But part of N is definite, so N to 2 is negative definite, and the Schur complement is positive semi-definite. Yeah, but the matrix N itself is not definite.
How these two construct such kind of matrix? N matrix?
Very good question. So we'll see in the next part of the lecture that in this data-driven control context, these conditions are naturally satisfied. I will also relate that to some conditions on the data. So it turns out that if you have some conditions on the data, then indeed these conditions are satisfied. Yeah. Any other questions? No? Okay, good. Yeah, so with that formula in mind, I can give some interpretation in what it means that the Schur complement of this matrix N is positive semi-definite. In particular, using the formula that we just derived, I now see that the Schur complement is positive semi-definite if and only if there exists a solution Z to this quadratic inequality over here. Let's also try to do that. So let's start with the if part. So for the if part, I'm assuming that there exists a Z. Now I use my formula, because this implies then that the Schur complement plus this term on the right this whole thing must be positive semi-definite. Okay. But note that we made this assumption that n-2 is negative definite. Which means that if I multiply with this matrix on the right and the transpose on the left, that this thing in general will be less than or equal to 0. So the only thing, so the only possibility for making this whole term now greater or equal to 0 is if, indeed, the Schur complement is positive semi-definite. Right? So this implies that indeed n11 minus n12, n22 inverse, n21 is greater or equal to 0. And that proves then, indeed, the if part. Great. Let's also do the only if part. So I do this magic trick. So for the only if part, now we assume, right, that the Schur complement is positive semi-definite. Okay, great. And what I need to prove now is that there exists a matrix Z. Maybe you can help me a little bit here. How would you choose Z, given the formula that we derived before? So I want to show that there exists this Z, right? Satisfying this quadratic inequality. If we can come up just with one Z, we're done. So how would you choose that? Let's have a look at this formula. I know that I can express I over Z transpose n I over Z as this Schur complement plus this second term over here involving the Z. We have assumed already that the Schur complement is positive semi-definite. So how can I now choose Z such that this whole thing is positive semi-definite, right? Because that would prove that this left-hand side is positive semi-definite. Sorry? Yeah, exactly. Yeah. Indeed. So we take Z to be minus n to 2 inverse n to 1. And then by our formula, you see that identity Z transpose n identity Z, since I took Z in this way, as suggested, this second part is 0, this cancels, I just obtain the Schur complement. That was assumed to be positive semi-definite, and voila, we have a solution. So indeed, the Schur complement is positive semi-definite if and only if there exists this matrix Z satisfying this quadratic inequality. No? Okay, good. Now, next my goal is to apply this in the context of data-driven stabilization. So I want to use this matrix version of the S lemma. And in particular, we can now use that matrix version of the S lemma to come up with necessary and sufficient conditions for informativity. Let's see how that goes. So I just remind you of the definition, since it's a long time ago. We talked about this S lemma in the middle. we saw already that the data are informative for quadratic stabilization if and only if there exist these matrices P and K such that this quadratic inequality holds for all AB consistent with the data, meaning satisfying this second quadratic inequality. Right? That's what we obtained before. Now, here we have a condition under which this quadratic inequality holds for all Z satisfying another quadratic inequality. And in fact, due to the matrix S lemma, that was equivalent to the existence of an alpha such that m minus alpha n is positive definite. Right? You see the structure here is very similar, right? Because here also we need that one quadratic inequality needs to hold for all AB satisfying a second one. So if you compare these two slides now, you may come to the inescapable conclusion that I did not pick these colors randomly. Because what is now going to be the idea? For the matrix M now, of course, we're going to choose this matrix in blue over here. And for the matrix N, in the matrix S lemma, we're going to pick this matrix in green. That's the idea. And then we just apply the matrix S lemma to obtain the following theorem. So, what is the result? Theorem says the following. We need to assume that the rank of x minus u minus is n plus m. So this is full row rank. Then the data are informative for quadratic stabilization if and only if, so if and only if, there exist k and p and a scalar alpha such that p is positive definite and the matrix inequality m minus alpha n is positive definite. So in comparison to the proposition that we had before, we now have an if and only if statement. Not only are the data informative for quadratic stabilization if you can find a solution to this matrix inequality, but also the reverse statement holds. But we do, for the moment, have to impose this rank condition on the data. Let's see how to prove this. So I already explained you the idea a little bit. I want to apply the matrix S lemma. So indeed, the matrix M is governing our Lyapunov inequality now, and the matrix N, that comes from the set of explaining systems, right? That's the matrix that is governing the inequality that describes all ABs consistent with the data. So, to apply the matrix S lemma, though, we do need to verify two assumptions. In particular, n to 2 needs to be negative definite, and the Schur complement needs to be positive semi-definite. So in the context that we have here, where we take this green matrix to be the matrix N, we need to verify whether the conditions of the matrix S lemma hold. So n to 2 needs to be negative definite, Schur complement needs to be positive semi-definite. So let's try to figure that out in the proof. So I now formally define this matrix N to be this matrix, depending on the data and the bound on the noise. And I partition that in the following way. So I write N11, N12, N21, N22. And yeah, the lines here in this matrix indicate the partition. What does that mean? Well, for instance, what is N11 here? It's this matrix above this horizontal line, multiplied with the middle matrix, and multiplied with this matrix transpose. Well, what is, for instance, N21? Well, that's the bottom matrix here, multiplied with this matrix in the middle, with this I over x, I next to x plus transpose. And finally, what is N22? Well, that's the bottom matrix here, multiplied with the middle matrix, with the bottom matrix transpose. So that's how I indicate that with the lines in the matrix. Okay. Now, for this particular matrix, maybe I can go back one last time. We, of course, need to verify now that n to 2 is negative definite and the Schur complement is positive semi-definite. Okay, the first claim that I make is that n to 2 is negative definite because of the rank assumption that we made. Well, let's see why that is the case. So the matrix n to 2, what is that? Well, I just explained it briefly, but it's this matrix 0, 0, minus x minus minus u minus times the matrix in the middle, epsilon squared identity 0, 0 minus identity, times the transpose of the matrix on the left. So there I get 0, 0 minus x minus transpose minus u minus transpose, like this. Okay, let's work this out. So what do I get? Well, for the first part, I get 0, 0. Then I get x minus u minus. And I still need to multiply this with 0, 0 minus x minus transpose minus u minus transpose. And if I do this product, you see that indeed you get exactly minus x minus u minus times x minus u minus transpose. Like that. Okay. Good. Well, why is that matrix negative definite? That indeed follows from the rank assumption that we made. Because if I now take an arbitrary vector x in R n plus m, and x is non-zero, I multiply this vector with the transpose from left and the vector itself from right. So what do I get? I get minus x transpose u, x minus u minus x minus u minus transpose times x. But this is minus the norm of x minus u minus transpose times x squared. So this is always less than or equal to 0, but because x is a non-zero vector and x minus u minus has full row rank, this product is actually non-zero, which means that minus this norm squared is now strictly negative. So the conclusion is that for all vectors x, this product is negative, for all non-zero vectors x. Hence, n to 2 is negative definite.
In that rank condition, I think there is another assumption that the time horizon we consider that must be greater than.
Indeed. Indeed, yeah. So if you have that this has rank n plus m, that implies that t needs to be larger or equal to n plus m. True. Yeah.
That is also an assumption in addition to that one?
It is a consequence of the assumption, because this rank condition can only hold if t is larger. Yeah. Any other questions?
If we don't make this assumption, then n to 2 is negative semi-definite.
True.
That does not work.
It does not work using this theorem. right? Because in this theorem, we make the assumption that n22 is negative definite. But what I'll show later on is that, in fact, there's a slightly more general version of this theorem, where you can also work with n22 is negative semi-definite. Using that theorem, then, you can drop this rank condition. I'll show that in the last part of the lecture. So in that case, this rank assumption is not necessary. Yeah, good question. Okay. So we were verifying these assumptions of the S lemma, right? So for now, we verified that n22 is negative definite. The only thing left to do is also show that the Schur complement must be positive semi-definite. But now I remind you of one thing that we've proven before. That's the following. Remember, if n22 is negative definite, which we've shown now, the Schur complement is positive semi-definite if and only if there exists this matrix Z satisfying this quadratic inequality that we've shown before. Aha. But now I know something, what we can do, because I just take Z to be the true system, AS transpose, BS transpose. I know that the true system is consistent with the data, so it must be in the set sigma of systems consistent with the data, meaning that this inequality must be satisfied. Great. So we know that indeed there exists a Z for which this inequality is satisfied, which, by the previous slide, shows that indeed the Schur complement must be positive semi-definite. Fantastic. So then we showed the two assumptions of the S lemma, namely n22 is negative definite and the Schur complement is positive semi-definite. Yeah, which means that indeed the matrix S lemma is applicable in this context and this theorem is true. So now the theorem follows from the matrix S lemma. Nice. Okay. Well, what I then want to do in the last part of the lecture is study some generalizations of this theorem. One immediate thing one can do, by the way, is, of course, this inequality that we see over here, again, is not linear in P and K, right? But we can do the same Schur complement argument as we had before to transform this into a linear matrix inequality, right? Because the matrix inequality is the same as we had before. The point was just to show now that it's a necessary and sufficient condition. So that's one immediate thing one can do. One can reformulate this as a linear matrix inequality. But now I want to study two more generalizations of this theorem. And the first one is a generalization of the noise model. So I want to generalize this assumption that the norm of W minus is less than or equal to epsilon. And the second generalization is going to be to rank deficient data. So indeed, we're not going to make this assumption on the X minus U minus data. We're going to drop that. And still, I want to obtain a necessary and sufficient condition for informativity for quadratic stabilization. How to do that? Well, first, I start with this generalization of the noise model. So recall that before our assumption on the noise was the following. So W minus times W minus transpose is less than or equal to epsilon squared identity. Because that was equivalent to W minus having norm less than epsilon. Yeah, by doing some matrix multiplication, I can equivalently rewrite that as this matrix inequality. Yeah, but now I notice the following, that instead of this very particular matrix that we have here in the middle, with this epsilon squared identity, 0, 0 minus identity, maybe I could try to generalize this and just assume the noise bound of the following form. So you see it's similar to the inequality that we had before, but in this case now I'm just assuming that we have this matrix phi, so So phi is a given symmetric matrix over here, such that the noise satisfies this quadratic inequality. That's a generalization of what we had before, because if I pick phi 11 to be epsilon squared identity, phi 12 to be 0, and phi 22 to be minus identity, then exactly I recover the previous bound that we had. Right? But there could be advantages of working with such a more general noise model. Yeah, go ahead.
One observation over there, you wanted every to be bounded. So that's why like basic structure is sort of some part is derivation.
True, true.
Here this more general bound. You put anything, any matrix over there.
Yeah, it may not be bounded, indeed. Yeah, very good observation. So indeed, the reason why the set of noise matrices here is bounded is because you have indeed this minus identity term over here. And then W times W minus transpose is less than or equal to something. Well, at least for the first part, I'm going to assume that this phi 22 is also negative definite. Some signatures is needed indeed. Yeah, that's true. Yeah. Let's study some special cases of this noise model. The first case is if we take phi 12 to be 0 and phi 22 to be minus identity. So this is almost the situation that we had before, but in that case, this noise bound boils down to the following. So we have the sum of W transpose. So we sum over all the noise samples from t is 0 up to t minus 1. This is less than or equal to phi 11. This we call an energy bound on the noise, because this sum over all noise samples, it can be interpreted as an energy of the noise. Previously, we were assuming that this phi 11 is epsilon squared identity. So indeed, if phi 11 is epsilon squared identity, then we recover the same bound as we had before. We can also study the noiseless case. In particular, if we have this bound with epsilon is 0, then of course W minus is 0. But we can also try to incorporate sample bounds on the noise. So imagine now, instead of having this energy bound, that all of the noise samples are bounded in norm. So I have a pointwise bound. Wt is bounded in norm by epsilon for all t. And that's different from assuming this energy bound. But if that sample bound on the noise holds, I do know that also an energy bound on the noise holds by taking phi 11 to be this epsilon squared Ti. So the conclusion is a sample bound on the noise also implies an energy bound on the noise. But the other way around is not true. So this introduces some conservatism. In fact, one of the tutorial, or the only tutorial exercise this afternoon actually, is going to be about the question how we can improve if we have only a sample bound on the noise. But the conclusion of this fourth part is if we have a sample bound on the noise, then we also can obtain an energy bound on the noise. By taking this phi in a particular way. And finally, I can also study bounds on the sample covariance matrix. So up to this moment, I have not assumed any statistics on the noise. It's just some noise that satisfies a certain bound. If the noise follows a certain statistic, then you may know something about the sample covariance matrix of that noise. And such bounds on the sample covariance matrix you can also incorporate by choosing the phi in a suitable way. In particular, what you have to do is the following. So you have to put phi 22 to be this matrix over here, phi 12 to be 0, mu you take to be the sample mean, so 1 over t times the sum of all the noise samples, And then you see that this matrix over here, which is called the sample covariance matrix, is indeed bounded by phi 1, 1. So conclusion is, by choosing this phi in a particular way, you can incorporate sample covariance bounds. It's just to give you some interpretation of what this noise model means and what kind of bounds on the noise you can incorporate using that. Okay. Now, the big question is, of course, we have a next class, I hear. Okay, well, luckily I hear that at 2 o'clock we can continue a bit with the lecture, and then afterwards we continue with the tutorial. So, since there is another class at the moment, we stop at this moment, and then we continue again at 2 o'clock. Okay? Thank you for the moment, and see you this afternoon.